All right, good morning. Today's going to be a little easier. I was thinking about it last night and I decided that dislocation and grains for people that are not material scientists all in 1 hour was a little much. Did you have anything, any thoughts, anything that you'd like to discuss on that? Because I went on it very quickly. The main thing, if you can remember a few things. The first one is that when you plastically deform metals, they do not soften. So what you see in a stress strain curve is associated with the necking. I think that's something that you should take out of this class. And also the fact that one of the reasons why all this is taking place is you have this multiplication of dislocation that we were talking about, and then you reach a certain point where there is so much that it's okay. Now it doesn't change anymore. And getting to that steady state quantity of dislocation is easier when you apply a cyclic load. That's what we were talking about yesterday, this nice image is by applying tension and compression on the sample. Or if you at temperature, and that's part of the reason why we do deformation processing, you get a flow stress that is about the same as you keep taking any piece of metal from the foundry and taking it down to an I-beam, a rod, or tin sheets used to make this stuff. So we'll talk more about forming. And what is very important in any forming operation is what happens to the microstructure. In the end, you'd like grain. So I'm just showing a grain here that's different from yesterday. This is actually a cross-section of the brass sample I passed on yesterday. And I don't want to make it look more complicated than it is, but the grain is this entire area, and what you see in it are just twin boundaries. So it's essentially a relatively low energy interface where you have a change in crystallographic orientation, but it's not a grain boundary. The grain boundaries are very high energy, they're very disorganized, and the twin boundaries is really more or less of a reflection of the crystal structure. The reason for showing this one, it is a single phase in this case here, and it's nice to have some idea of size. So when we're talking about 100 micrometers for this type of alloy, it makes sense that when I deform it, I don't really see the roughness. So when we were looking at those copper samples yesterday and we were seeing all that orange peel effect, it's because the grains were bigger than 200 micrometers approximately. We talked about how with increasing the temperature, you go from these very deformed microstructure, if you went through a cold working process, and then you initiate very small grains that have very low dislocation density. And the process of generating those really depend on your temperature and your level of strain, and then eventually, we haven't really talked about this too much, but if you raise the temperature too much, then the grains will continue to grow from the recrystallized. Yes?
Is it generally the common theme that grain size is smaller during castings compared to, say, extrusions or other processes of forming metals?
Okay, so what happens in casting in general is you get bigger grains, especially the dendrites. Each dendrite is more or less of a single grain that's growing and keeping a certain orientation that grows very quickly. You do get relatively fine grains in aluminum castings that I've talked about just a little bit at the beginning, because you have two phases. So if you're going to solidify two phases at the same time, and eutectic, and that ties into one of your questions from the end of the class. So let's go through this, because that's why we use aluminum silicon. We can get relatively fine grains, and the reason is we solidify two phases. So say I have the aluminum and silicon instead of just growing. So I have the solid here, and I have the liquid, and I'm growing essentially, if I'm locally, what I'm doing is I'm gonna grow the alpha phase and the beta phase by just moving ahead of the solidification. I'm just moving the two elements in opposite directions. So one phase is going to become silicon depleted, and the one next to it are going to have more silicon. That way you get a very fine grain size right from casting. But if we're talking about steel, if you remember when I was showing the image of an ingot, the ingot is this big, and you can see the grains visually from the solidification, so they tend to be very large. Yes?
Wait, forgive me if I get the terminology wrong. This lamellar structure, is that what that is? Between
Yes.
the two phases?
Yes.
The lamellar structure, does that mean though that you just have very long and deep grains, or do you actually
Yes.
get like the nucleation of new grains on them?
The microstructure can be even called needle type eutectic, because each layer is very thin. Now, you can think of it this way, like this is a casting process. Now, if I heat this up, I can grow the layers, and then all of a sudden they look bigger because the smallest one just disappeared and created a bigger one. So I can end up, depending on my casting rate, I'm going to end up with bigger or smaller interfaces just by how much diffusion I'm going to allow, essentially, how far the alloying elements are going to travel.
Does that happen with the two-phase system or specifically with the eutectic?
Eutectic and eutectoid, which I'm sorry, but such is life, okay? Eutectoid is similar, except it's specific to steel, and we'll go through that. We'll make sure we get back to that. But for now, let's just think relatively simply that we have a liquid, we have a solid. If we go really fast, this movement here can't go really far, but if we go slowly, then there's going to be more separation. And it's used, and it's one other reason why we use aluminum silicon, because as cast, they're relatively fine microstructure. It's still not super ductile, but it is a fine microstructure with a relatively high strength as compared to, if you're to cast pure aluminum, really, it's really soft and difficult to shape and do anything to it. Yes?
Yeah, I have two questions. A follow-up question to that is like, how much does the initial structure from a casting influence like the final microstructure after cold work and hot working, whatever you do?
If you're doing your deformation processing correctly, fairly little. Fairly little. What's important in the casting is make sure that you don't collect too many inclusions, because these you can't really get rid of. You can just break them down and make them smaller. It's a problem with casting aluminum. So aluminum for aircrafts tend to have a relatively low fracture toughness in the transverse direction, because as you go from the big billet down, you smooth down the inclusions, but they remain there and essentially kind of pre-crack. And you can have a fracture toughness that's only half if the crack goes in the direction of these inclusions as opposed to transverse to it. So there is, all I guess I'm saying is there is still an importance in doing your casting right, but not in terms of the grain size. Yeah, if you have segregation, so if all your alloying in the element is in the middle, you're going to have to do more deformation processing to get all that chemistry distributed evenly through the thickness. Very good question. Yes?
I feel like this clock, there isn't really like a time dependency included in there. Is there a time dependency?
Yes. So typically, life is not exactly like you're going to go and heat up instantaneously and be at that temperature and do your recrystallization process. Depending on the process, you may be able to heat up quickly if it's radiant heating of the sheets and control it. One thing to keep in mind, of course, is the difference between the kinetic of the growth. So if I manage to have very, very little of these initiation site here, and then I heat up and they grow quickly, that's where I get the anomalous grain growth. If I can only allow for just a few to really pop and start, and then they continue to grow is the worst case scenario. So heating rate matters, and then of course the whole history of the process. Typically though, you try to do it almost at constant temperature and wait. If your desire is just to recrystallize, there's a certain range for an alloy. It's not as complicated as it may seem. You just get to a certain temperature, and then you wait an hour or less, and you're done, essentially. Those we were looking at, the copper pieces, they were 1 hour in the oven. Yes?
Just, I guess, a quick follow-up. Does recrystallization work the same way with the lamellar structure as it does with something more phase? How does that translate?
Well, okay, so very, very different. The reason why we recrystallize here is because we deformed it in the first place. Over here, this structure, you get it first when you are solidifying or transforming the steel from very hot to cold temperature. Now, when you have the kind of low temperature steel and you deform it, they will remain, well, there's very little deformation that's taking place in this phase. And you're going to have to, for the steel, it's very rare that you're going to just recrystallize without essentially remelting all of this. Because there is this, yeah, we can do it now because it keeps coming back. So what happens with steel is, if you remember, let me make sure I get enough space here, I'm sorry. All right, so the steel has the cast iron. So over here, we have the cementite, that's the beta phase. And over here we have the alpha phase, that's just pure iron. And what happens in this region, I'm exaggerating it, but and this goes further up and down. Does that look right? Yeah, just right. Okay, so over here, you have a solid, that's the austenite, that's red steel, that's going to transform into the cementite. So one phase going into two phase, but instead of being a liquid, like we have over there with the, that's a higher temperature, you have over there with the cast iron, you're having it at a lower temperature, everything is already solid. And typically for steel, if you're really going to soften it to go to a subsequent process, you go back here and essentially recrystallize at that point. It's all blended together, and then you cool it down again and go for it again. So when we talk about hot working for steel, we only have one phase. And that's why we talk in the product about the grain size. We tend to think of it as the size of the austenite grain for controlling the structure. So what used to be one phase has a certain size, and that's what we think about in terms of grain size, even though it's multiple crystals. Well, I'll show some images. They're better than my drawings. All right. This is great because to some extent the alloy that we do the most rolling of, as you've learned from Dr. Eager, is steel. So understanding a little bit of how all this works. So you're at very, very high temperature. I have to continue this so the liquid is here, and I'm just missing a portion of the diagram here. You go from the liquid, you cast it, and then you heat it up. You try to be in a zone where you're very ductile and you can have all those processes of recrystallization continuously taking place. So that's why over here, in terms of strain, what you see with the stress level, the flow stress, it becomes constant. So in effectiveness, the steel is becoming a little bit like a viscous fluid. You keep deforming it, and it's keep resisting the same amount. If you try to go faster, it will get harder. So there is a certain similarity. It is solid, but the behavior is somewhat similar. You go faster, it gets harder, and you slow back down again, then it goes back to where it was. So it's a nice property in terms of having all these processes being in steady state, essentially. And we will start with rolling because, again, that's what we do a lot. We do a tremendous amount of rolling. And I showed you a little video last time, but the first thing with rolling, if you go to a rolling mill, is you can chat and have a nice time at the beginning when you heat it up and you start deforming it. And the reason is typically as the steel goes through the process to be thinner and thinner and thinner, it goes faster and faster and faster. The first reason is conservation of volume. So if I'm looking at this as a sequence, I have something that's very thick that's thinning down on the image. I'm exaggerating a little bit. This is a factor of 2 reduction. That's a little high. But the idea is the speed here, in this case, is twice what it was over there. And it's not exactly realistic, but again, the work pieces, they just keep going faster and faster. The other reason why we do it this way is as you get thinner, you have more surface per volume exposed for the radiation loss of heat. So if you don't want to heat up your parts, you need to continue to go faster and faster, otherwise they will cool down, essentially. So it can come very fast at the end, in the sense that you need guide, because if something was to fall outside the rail, it would be dangerous. In terms of what happens between the rolls, I thought this would be of interest to you, that you have a certain angle where you get most of your pressure, and therefore you have essentially more wear at that location. If it's a roller, it's fine because it keeps going all around, but this concept applies to extrusion and drawing, all of these processes with metal. You have to think about lubrication a lot, and you need to think about how you're going to control the temperature of all these rollers. Are you going to cool them, or is it okay to let them continue to get hotter until you reach that steady state? And it depends on the process, but Professor Eager has a full 12 hours online just on forming. And therefore, he goes through a lot of details with respect to the lubrication and how to essentially estimate for each process how much reduction you get each time, what's acceptable as a reduction ratio. I'm just really trying to give you a sense. So, you know, if you in your mind, when you think about a piece of steel that's being hot rolled, you think about, well, you know, there was a lot of steps involved, and one of which is how much you reduce each time, what temperature you're going to process at. It's going to influence my grain size. If I'm not well lubricated, I get wear. I may have some surface defects. It's typical when you make treads. Treads, you need a lot of lubrication if you're going to forge treads. If you don't, you get reentrant corners, and these tend to favor a lot of crack initiation. Same with forgings. Forgings, I have one here. This is, I could have passed it around asking you what you thought it was. It's a forging in which they machine the internal tread, and I can go through later about why they've done it this way. This is something, if you remember, I already mentioned yesterday the difference between hot working and cold working. In cold working, like the aluminum wires, the copper wires for electrical power lines, you increase your strength. So when you finally form, you can't go through a heat treatment with pure copper or pure aluminum. It's only going to make it softer. So if you want strength, And that's also the same for stainless steel. This is stainless. So if I take this beam, and it's an austenitic stainless steel, essentially a steel that remains a single phase here, I can't make it stronger by heat treatment. It's just not going to happen. So the only way to increase the yield is by cold working. So you get better dimensional tolerance. You can do cold forming. For example, this is cold form here, the head of that bolt. I'll pass that around too. And it's galvanized if you wonder the surface feature of it. It's the most common grade of ASTM A325. It's the most common grade of structural fasteners, bolts. The cold forming operation doesn't mean, in this case, you try to do it at once, but sometimes you can do an operation, you heat it up, and then you come back and finish it. Sometimes you can have multiple operations that are cold just to go progressively using different dyes. That's very typical. So hot working is certain characteristic here. We talk about temperature of above 0.6 of temperature of melting. If you remember if you know anything about metals or materials in general, they will start to creep. They will start to deform under just a dead load above 0.5 of the absolute melting point. So when you're looking at 0.6 here, that's the same condition. It means the steel at the temperature where we form it, if I just hold it, if I just put a dead weight, it's going to continue to stretch and stretch and stretch. A little bit like a polymer does at ambient temperature. The reason the polymer does it at ambient is that you can think of it as just the temperature of melting is much lower. So you're above that 0.5 temperature of melting. All right. There are a lot of forging operations and forming operations. The extrusion, this is typically made by extrusion. Yes?
I just want to make sure that I understood. With that stainless I-beam.
Yeah, there's a trick to that one. It's not rolled.
Okay.
But think of it as roll. It looks the same.
Fair enough. I guess that was kind of maybe part of it, but the reason that you can't heat that up for more strength is because you don't want recrystallization or any of that. Or would you actually get
Oh.
because you heat it and dip that?
Okay. We're going to stainless steel right now. If we are a stainless steel that's not magnetic, that's actually a way to verify. So if you want to know if you have the cheapest stainless steel, if you have a higher quality stainless, you put a magnet to it. If it's not magnetic, it's not the typical steel, right? Most steel are magnetic, ferromagnetic. So when it's not magnetic, it means that it managed to remain in its, if you look at carbon steel, in the high temperature phase. And the reason is you added nickel and you added a few alloying element, a little bit of chrome that just extends the range of stability of this phase. When you're a single phase and you heat up, the only thing that will continue to take place is the recrystallization and the grain growth. And that will only reduce your yield strength. So it will only soften it. In steel, it's very different. In carbon steel, because of that transformation, when you go from here and you make all those faces, there's so many things you can do. And we'll start talking about that at the end of today. Forming steel. Okay, so now you're going to wonder. You look at it, it's very square between the two cords here and the web. And the reason is, it's a new process that they were using to make custom shapes where you essentially start with 3 plates and you laser weld the corners. So I can pass it around. I didn't have a rusty one. This is the only one I carry around. If it's made by rolling, I think you can think of it as it will make more sense to have a more rounded corner like this, because it's easier to make and you have fewer risk of causing any kind of re-entrant corner if it's rounded here, essentially. So that's an S type of I-beam, and then we started making wide flange that have this a little sharper just by improving all the rolling technologies, the lubricants and all that, but you still have a radius here that is much bigger than what you have in that laser welded beam. Extrusion is this one. So you start with something solid and you essentially throw it a little bit like you can make pasta or shred beef. You just go through a channel and then you get a piece on the other side. This particular one, you see all these holes that was riveted. It's a failed piece of the internal structure of a small aircraft wing. And there are a couple interesting things to it. One is you'll see some elongated hole. These are not from the drilling process. They are from loose rivets that just grew and extended the hole. And when you lost the support, you had a break on one side, so there's actually a fracture surface on this side here. Because you lost support, so you had bending. And this was intended to be really tension compression. Deep drawing. The aluminum can is a good example. What is very particular to deep drawing is all that material, so when you go around the corner, it's bent, but then it has tremendous tension. So you do need your material to have a lot of hardening. So if you're going to do it on steel or brass, it's very typical to stop in the process, cool it off, heat it up, and to soften it, and then you continue. Because you want to continue having enough hardening. If you lose the hardening, it's like our tensile test. You have that local instability, and then it's cracking at one point. So the aluminum is the same. You use aluminum alloys that will harden during deformation. If you try to do it with pure aluminum, make a can, it's just not going to work. Not enough hardening. Yes?
Is there ways to shear without getting burrs?
Shear.
So if you like cut a piece of metal, you're always going to get a burr.
Oh.
Is there ways, so like if you preload two surfaces?
Well, if you if you use cold work products, you have a higher yield strength, but you have less hardening. So by the time you reach that critical shear stress, it's going to fracture more easily. I'm not sure we use it too much for shearing. I mean, on a professional shearing machine, you can really minimize it by tightening the distance between the two parts to something that most people will not consider a problem, I would say. But if you think of it just in generally in terms of the resistance to shear, the resistance to shear is very important in machining operations. And that's why we use sometimes resulfurized steel or brass that contains lead, because the small lead particles just enables the formation of these voids, and it's easier to create that shear plan. So if you take leaded brass and you shear it, it's going to be a lot easier, the same way that it's easier to machine. Bending, we're not going to go through it in a lot of details. I guess I'll just say it's used a lot as a forming process, sometimes just to bring a little more stiffness to a sheet metal. It avoids having to make joints. You can do very complex geometry nowadays through bending processes. The stretch forming is probably something you're less familiar with, so I decided to show you an example that I've seen and dealt with quite a bit. Stretch forming. So you essentially grab the sheet of aluminum and you pull on it and you press it against a very predefined shape to make these complex geometries of the aircraft fuselage. If you were to try to do it through other processes, like for car body panels, typically you use stamping. But what this allows you to do is end up with much less spring back, because as you stretch form, everything is loaded in tension as opposed to having bending. If you bend something, it's going to bend back. But if you stretch something and everything is plastic, you let it go, it tends to be just exactly the same. So for thin members in aircraft fuselage, it is the most common process. So you can do a double curvature relatively easily, and then the stretching operation also helps you with the heat treatment, and we can go through that next week. Actually, we'll go through the heat treatment of aluminum. Yes.
So you get less spring back because you've already reached the yield zone, so you don't have proportionally as much. Because like when you go up the stress strain curve, you're always going to come back.
Yeah, let's think of it this way. If I'm looking at just a plate here that I'm bending or stretching, so if I have this plate and then I'm putting a bending moment on the end here, this way, and I look at it on a cross section, what I'm seeing is this is the plate in cross section. I got tension on one side, and I got compression on the other side. And then I got all sorts of strain hardening. When I let that go, these forces are going to zero, these forces are going to zero, but overall I'm deflecting. When I'm stretch forming, the advantage is through the cross section, everything is in tension. And hopefully it's just about the same tension through the thickness. So when I let it go, there's really nothing that takes place. No change, no bending. Yeah, if you bend, you agree you're going to have a side and tension and then compression. That's a typical stamping operation. When you stretch form, you're in tension on both sides. So internally, while it's in full load and it's right against that complex shape that you're looking at, the tension through the thickness is approximately the same because you deform it plastically. So you exceeded the yield strain. Initially, it's going to be different, but as you keep deforming, because we have the Hooke law, so we're thinking here of Hooke law because we have tension and compression. But when you get in tension between here and here, yes, you do get the differential strain that allows you to bend. But when you're looking at the stress level, so to be fair, and make sure you agree with me, I'll just put a little gradient here because of the strain hardening for creating the curvature. So in the end, this is essentially your bending moment that's going to be with you when you unload, and over here you got it going much bigger.
So you cut it in half because you're essentially going down the elasticity curves the same way.
Oh, it's much less than half. I would say you're cutting it down 80 to 90%. It's very useful. I mean, they wouldn't do it if it wasn't for both getting the dimension very precisely, because when you try to get these parts to put the rivets on, if you have to hold them and push them, now you're talking about it having a spring in your fuselage, and that's going to make it crack more easily. So you want it to be as stress-free as possible when it's all assembled. It's not that I couldn't take that sheet and just slam it on the frame of the aircraft, but I'll have that tension and compression when I'm done with it. Some of it stays. That's the problem. When you have this here, it's not exactly linear because you have the deformation taking place. You have more deformation here, and you have more deformation there. So there will be built-in residual stresses in this configuration and very little in that one. Forging. We already talked about the case of the head of the bolt, so I'm not going to go through too much detail, other than saying, you'll take in forging, you can just really make a simple part, but the reality is you can make it very, very complex. A little bit the same way, if you remember the example of the die caster where I had pieces of the mold coming from the sides on the video. In forging, you can have the same. There's nothing that prevents you from having rams coming from all directions with multiple die, so you go gradually to a better and more complex form. One of the biggest issue with forging, of course, is the volume of fabrication. To make all these dies and determine the process precisely, it's very, very expensive. So you can forge, they forge components. We worked on a project where they were forging the base plate for electrical panels. That was Siemens, I think, or their competitor. And to make the tabs and all this, there's just a lot of operation. They wanted offset and all that, so they were using a 2 or 3 forge operation to make a complex shape out of aluminum. And if you have a little change in your input material, so all of a sudden you buy a grade that's a little softer or a little harder, it's got a little more alloying element, they had to adjust because the behavior was very different. So it's something to think about. It's not only more complex to set up in terms of getting a consistent quality. The consistent quality here, especially if you, whether it's hot, cold or hot, how the material is going to behave is very different depending on the alloying and the prior history also. So it makes it very challenging, and it's only used for high volume application where you can afford the extra cost to get better properties than you get out of castings, for example. So that little piece I had, it's essentially an adapter that you put on a pressure vessel, you weld it on the pressure vessel, so you can tread in, on the inside of that piece, you can tread in a riser. It's going to be subject to a lot of stresses. It needs to be weldable. So there are a lot of advantages in having it forge as opposed to cast. You could machine it if you only needed a few, but if you need a large quantity, I presume that's the reason why they use forge. One way you can tell it's forged, I can pass that around one more time if you're interested. Did it end up over here? Yes. Oh, all the stuff's here. You can see the little lip here. That's why I actually didn't go back to the manufacturer to verify. You've seen it, okay. So these lips, are useful. The markings, when you see the markings that are really formed, typically it's either a forging or a casting, and then you have to look for other features to differentiate between the two of them. One thing that was always, I wondered about that for a long time before I found and got involved with more details of it, how you make tubes. There are many ways to make tubes. One of them, you start with a plate, bend it, and then you just have a resistance weld. It's the most common way to do it. For steel, what I've learned not that long ago is a lot of times they call it seamless, but at some point in the history it was still a plate that the fusion welded, but then they continue to draw it such that you can't tell. You can cut it up and you can't tell that there was a weld on there to begin with. And it's discussed in the ASTM standard. So, it's true. It says seamless. It doesn't say weld-free. So it's got to be. We have to give them that credit.
It's the ASTM standard.
Yeah.
For seamless weld.
Yes, a seamless pipe. Yeah, they go to the detail that a seamless pipe essentially, well, there's also the difference between seamless and seam-free, okay? So there's this zone that is can be very hard to identify, and they have techniques, I think, in there they describe to see if it's acceptable or not, the amount of further drawing that you had after that operation. I was just very surprised to see it because, you know, it seems very obvious. Well, seamless, okay, so I don't have to worry about the seam. And it's true, I'm not saying that it's a problem. I'm just thinking about how we think of it. It's not necessarily that it was a solid piece that they really went with a mandrel to make it a form piece. So I'm showing here a few examples. We're using a plug or a mandrel to finish a tubing. So you already have something, and what happens with drawing and use the mandrel, you can really control your tolerances very well. So if you, through a prior operation, manage to get the hole, or you form it like we discussed, you keep straining it, and you can do it hot, and that's how you get your diffusion, you get recrystallization, and you can't tell that it was welded a while back. A similar process that I also, when I've learned of this, I found very interesting is it's PEX tubing. Professor Eager brought some of it in class, just a little semi-transparent plastic. The difference in this process in the middle, what it is you have PEX, you have aluminum, and then you have PEX again. How did that all happen? It happens in a single operation where you come with the sheet, two sheets, you have the two sheets of PEX coming in, it's really hot. And then you have the aluminum also coming at a sheet. So you start folding the inner layer, coming back on its own, so you kind of have a hot seam there. You come with the aluminum, you spot weld it, and then you come with the outer layer, and in the end it gets extruded to give you something that looks really nice in terms of a cross section. And it's seamless, and it's all happening at once. The reason you can do it, even though it's cross-link, is the way you do the cross-linking in this situation is you put a little, the cross-linking agent is activated by humidity, and you put it at the very last minute, so when you do all this forming and you make those interfaces, it's not cross-linked yet. It's going to cross-link when you cool it off. So it's kind of just to show you, there's always a best way to make these things, and that's one when I realized, I was like, okay, I guess I understand why they sell it for just a little more than a regular PEX tubing, because they can really make it efficiently by this process.
What would this type of tubing be used for?
Yes, so the reason for the aluminum is to act as an oxygen barrier. What happens if you have radiant heating system and it's circulating hot water through a burner, if you keep feeding oxygen into your burner, you'll corrode it very quickly. So most systems, heating system, are essentially called closed loop. So the water that's inside has some oxygen at the beginning, it starts the corrosion, and then there's no oxygen anymore, and therefore you don't have any corrosion. But if it's just PEX, there's too much diffusion of oxygen through the tube wall, and they were corroding through the burners way too quickly. And there's really no easy additive that you'll add to the PEX to make it really resistant to oxygen. You can put all these nanoparticles in it, you get some benefit, but in the end it's not like an aluminum layer. The other advantage, sometimes they were using it for potable water, because if you bend it, it doesn't spring back on you as much. The aluminum deforms and keeps the shape. So in floor heating, you'll have these S shape going under the floor, and it's easier to make it with this, and you don't need as many staples to hold it in place than if it's just a PEX tubing. Yes?
So why do they choose aluminum as the barrier?
As opposed to what? You need something that's very resistant. So it tends to be a metal. You need something that's very flexible. At the same time, you want to prevent the flow of oxygen. So metals are, very, very good diffusion barriers. And I guess within the metals, Aluminum is very ductile, and it's available in very thin shapes. It's generally corrosion resistant. There was also moisture, of course, penetrating through this wall. The reason I got involved with this, they had so many issues because they thought they would design it really just for radiant heat. So the resin they were selecting for the inside was not really oxidation resistant. They didn't put enough oxidation inhibitors in that resin. So when people were using it for potable water, it was just degrading too quickly on the inside. I went beyond. It's easy to get sidetracked with stuff that's exciting to me anyway. All right, this is the better drawing of the whole phase diagram. This is a good way to think of, because we're going to switch gear a little bit. We're going to talk about heat treatment next week. What happens in heat treatment is different if it's steel, for example, than aluminum. Very, very, very different. I'll talk about steel first because most of you probably heard of quenching of steel, that it's changing the behavior a lot. So you take the steel, you heat it up until it's really red. That's this phase here, that's the austenite steel. And then you cool it down quickly by quenching it in water or oil. In some alloys, not so much steel, but in some alloy you can also just use airflow to cause enough cooling for quenching. The reason for trying to use oil instead of water, trying to use air instead of oil is distortion. Because when I take the piece of steel and I put it in the water, the outside gets really cold quickly, the inside stays warm, and if I have different thicknesses, you get distortion. Now, when I'm talking about cooling it off quickly, is you cool it off quickly enough that what you form is not in the phase diagram. And that's the martensite. And so I think you asked about a phase transformation or deformation that will cause a volume change in the material. Well, to some extent it's associated here, because if I'm going from the austenite here, the single phase, to that phase that's not in the phase diagram, it's the martensite. It's a tetragonal structure. It's not as deformable as these cubes that I circulated yesterday. If you do that, you get a volume increase of about 4%. So that's another reason for getting distortion. So it's not, it's not a perfect world. There are a lot of trade-offs, and what I also want you to keep in mind, and we'll go through that in details next week, is there are very, very few pieces of steel in the market that are quenched steel, that are martensite, because it's too brittle. But it's an intermediate step to go to a good compromise in microstructure. So you start with something soft, you make it very, very hard, and then as we'll discuss, you heat it up again to get the compromise. And that's what we call high strength and super high strength steel. So that will be, we'll do aluminum next time, and then we'll do steel the following time. There's definitely enough to really, so at least you can remember something after the fact. Thank you very much.